This time, on the bench is a pocket watch from Omega. Let's begin by opening the case. Both the caseback and bezel are friction fitted. I'm using a simple knife to gently loosen them, being careful not to scratch the surface. The next step is to remove the hands. I cover the dial with a piece of plastic to protect it. My go-to tool for removing hands is these two levers. I get the most control out of them. Here comes the dial. It will be cleaned later on with some denture cleaner, since this is an enamel dial. Now, let's take off the dial washer and hour wheel. For the Canon pinion, I am using a Presto tool. Here is the movement. Like always, the balance is the first part to be removed, as it has very fine and fragile pivots. The movement is quite nice looking. The plates and bridges are all covered in what's called perlage. It is also known as circular graining, and it is a finishing technique consisting of a series of overlapping, small, circular patterns that create a textured effect. Perlage first appeared in the late 18th to early 19th century. It was initially introduced as a purely decorative technique. At the time, perlage was done entirely by hand using simple tools. Artisans would manually rotate a small abrasive-tipped wooden or metal peg, often a drill or stick covered with emery powder, to create the circular patterns. The work required precision and patience, as the circles needed to overlap perfectly to achieve a consistent aesthetic. This method was time-consuming and required a highly skilled watchmaker to execute. In contemporary watchmaking, perlage is still widely used, but is often applied using more advanced and efficient techniques and materials. While some high-end watch brands continue to perform perlage by hand to maintain traditional craftsmanship, most manufacturers have transitioned to semi-automated or fully automated processes. Modern perlage is typically created using a CNC machine equipped with a rotating abrasive head or a fine brush. On the top right there, you can see a serial number. With that information, an approximate year of manufacture can be found. In this case, the serial number dates the watch to 1924. This pocket watch, like many other pocket watches, was made before the standardization of spring shock system. The balance jewels are fixed using simple but very tiny screws. Likewise on the other side of the plate. The final step is to open the barrel and remove the mainspring. It looks quite old and pretty dirty. What's surprising is what's at the end of the spring. Someone has made a rather unusual creation. I suppose what happened is that the spring broke there, and instead of replacing it, the previous watchmaker found a way to put the two pieces back together. The disassembly is complete, and all the parts are ready for a good cleaning. I'll be right back after I give them a good scrub and throw them in the cleaning machine. Now that the parts are all clean, it's time to put them back together. First, we'll insert a brand new mainspring into the barrel. This mainspring has a T-end shape to fit perfectly into the slot on the bottom left corner. The mainspring barrel is now ready to get back on the plate. Omega is one of those names that instantly comes to mind when you think of Swiss watchmaking, and for good reasons. The company's story began back in 1848, when Louis Brandt started making watches in La Chaux-de-Fonds, Switzerland. Back then, he was assembling pocket watches using parts from local craftsmen, and his creations quickly gained popularity across Europe. Fast forward to 1880, after Louis Brandt's passing, his sons Louis Paul and César took over the business. They moved it to Biel, where Omega still operates today, and introduced new production methods to improve precision and efficiency. The real turning point came in 1894, when they developed the 19 lines Omega caliber. This wasn't just a movement, it was a game changer. Its design allowed components to be easily replaced, setting new standards for watchmaking and repair. This innovation was so influential that the company adopted the name Omega in 1903. In the early 20th century, Omega started making a name for itself in precision timekeeping. In 1909, they were chosen as the official timekeeper for the Gordon Bennett Cup, an international hot air balloon race. By the 1930s, they were dominating observatory trials with record-breaking precision. During this time, they also supplied watches to the British Royal Flying Corps in 1917 and the US Army in 1918. In 1932, Omega launched the Marine, the world's first true dive watch. It was groundbreaking for its water resistance. Then, in 1948, they introduced the Seamaster, which remains one of their most iconic lines. You'll notice that I removed the barrel bridge. The sliding pinion can only be fitted from the backside, which is not the usual case. Anyways, only piece missing is the pallet fork. Fitting this piece will close the energy circuit. In 1952, Omega debuted the Constellation line, a more luxurious line, and in 1957, they released the legendary professional trilogy, the Speedmaster, Seamaster 300, and Railmaster. It's now time for regulation, and some work awaits us there. Let's check the raw numbers firstly. The amplitude is good. Let's begin by fixing the beat error, which is the difference in duration between the clockwise and counterclockwise swings of the balance wheel. In this case, it must be done directly on the collet of the balance wheel. By slightly rotating the collet, I can fine-tune the position of the balance spring. Here's the result. It's much better. Now let's focus on the rate. I have noticed that when measured in different positions, the rate varies by big margins. This means that the balance wheel is wrongly poised. This is going to be addressed using what's called dynamic poising. Here are the 4 main points of this technique. Firstly, we need to make sure that the conditions in order to use this method are met. A sufficient amplitude, and a rate in dial up and dial down position similar. These are good. Now, point number 2 is finding the heavy spot in the balance. In order to do so, I'll need to release the mainspring so that the movement is at an amplitude of around 150 degrees. The reason for that is found in this book, which is a reference in watch regulation. It was made by Hans Jendritzky, a German watchmaker of the 20th century. This graph shows how poise errors interact with amplitude to affect rates. The x-axis shows the position of the heavy spot, the left y-axis shows amplitude, and the right y-axis shows rate. This figure is a goldmine for watch adjusting. It tells us that poise errors are largest when amplitude is low. Poise errors are bigger when the heavy spot is above or below the balance staff, and smaller when they are to the side. At low amplitudes, a heavy spot below the balance staff causes a gain. A heavy spot above the balance staff causes a loss. Poise errors are equalized when the amplitude is 220 degrees. When amplitude exceeds 220, we find small poise errors in the other direction. I am now releasing the mainspring to reduce the amplitude. After that, I'll check the 6 positions, and as said earlier, the heavy spot is located below the balance staff in the fastest position. This isn't as complicated as it sounds, bear with me. So let's begin and measure the different positions. This position is the fastest. To be as precise as possible, let's check the 2 adjacent positions. This confirms the fastest position as being this one. The third point is about tweaking the balance. In this case, the dial up and dial down positions are fast, so I'll be adding weight to the opposite side of the heavy spot to balance it all out. This process will be repeated accordingly to the measures that we get and will end when results are deemed decent. Let's get to it. So here is the heavy spot. I will be adding weight on its opposite side. The way to do that is to use timing washer and fit them in between the screw and the body of the balance. However, these are hard to come by, and I do not have any with me, so I'll make them myself. I will be using a dial washer. These are very small scales that I am dealing with. Just look at the size of this screw. In order to make the timing washer, I am making a small hole in the brass so that it fits in the screw. After that, I will be cutting the excess material with as much care as possible. Now it's time to fit everything back together with the timing washer in addition. Since the screw is so small, the best way to get it back on the balance is to use a vise. It simplifies the process by a lot. Let's check the results. I am focusing on 4 positions: dial down, dial up, pendant up, and pendant down. Let's check the results. I am focusing on 4 positions: dial up and down, and pendant up and down. Here are the final numbers. I am satisfied with what I got, especially considering that this is a 100-year-old timepiece. The delta is the difference between the 2 farthest mean rate measures. Here at 7.75 seconds is pretty good. The rest is also very decent. The regulation is now over, and it's now time to resume the assembly. The dial has some stains all around it. In order to clean them, I am submerging the dial in a denture cleaner. This can be done only to enamel dials. After some time, the dial is rinsed and now looks much better. I decided to put a brand new glass on the watch. I used this crystal press that bends the glass evenly so that I can fit the bezel onto it from under. I then release the pressure to allow the crystal to take its shape back and sit properly around the bezel lip. Final stretch now. The hands are back on the watch and the hole has been cased back together. This is it. The work is now completed. It has been a pleasure working on this pocket watch. It is now ready for the next 100 years to come. Thank you for sticking with me through this session. I'll see you in the next one.